Welcome to section P.1, where we're going to start out our week 1 on algebraic expressions, math models, and real numbers. So let's get into some definitions and kind of look at some of these things on out. So first thing that we look at in an algebraic expression is that we have a variable is a letter that is used to represent various numbers that are unknown. Okay, so that's what we're always looking for in a sense. And we, a lot of times when we're solving, are looking at finding what that unknown number is. So, again, kind of starting off basic here, we're going to get also the idea of an algebraic expression is a combination of variables and numbers using the operations of addition, subtraction, multiplication, and division, as well as powers or roots. So a lot of times you'll see things, even just if I just do an x, that's an algebraic expression. A 3x minus y, that could be an algebraic expression. I could just have it in one variable with the number as like 2x plus 5, and I can also kind of throw some things in here for a fraction in a sense and make it an algebraic expression. So something like 4x squared plus y all over a 2y plus 3. Now, the idea of this, when we start talking algebraic expressions, sometimes at the very beginning we kind of look at doing some evaluating of these expressions. So in order to do that, we're going to kind of look at what it means by an exponential notation. So on an exponential notation, let's start off by saying if n is a counting number. Now we haven't gone over the number systems yet, but counting numbers are pretty easy, where they're 1, 2, 3, 4, etc. Then if I look at b to the n, what does that mean? That means that I'm going to take that base, call it b, and I'm going to multiply that number n times to get the product, okay? Where b is what we refer to as the base and n is what we refer to as the exponent. So a lot of times people will mess this up and do b times n. You don't want to do that. It is just b times b times b n times. So for example, if I said 8 to the second power, or sometimes we say 8 squared, then that's going to be defined to be 8 times 8, which gives me 64. If I want to look at 2 to the third power, or we say 2 cubed, then that is going to be referred to as multiplying 2 by itself 3 times, which in the end gives me an 8. If I then want to look at 3 to the fourth, again, that's not 3 times 4. It's going to be 3 times 3 times 3 times 3, where it's 4 times multiplied by itself, and that will give us an answer of 81. So make sure you don't make that mistake of doing the base times the power. It's the base multiplied by itself, the number of times of that power. Okay? So with an algebraic expression, like I alluded to before, we can use these to evaluate what it is. So finding the value of an expression for a given value of a variable is referred to as evaluating the algebraic expression. And this can involve many operations. Thus, one must follow what we call in math the order of operations. So, there's two ways to kind of look at the order of operations. One that I was learned or taught as, they refer to it as PEMDAS now, but I always said, please excuse my dear Aunt Sally. So the P represents parentheses or grouping symbols. The E represents exponents. The M means to multiply. D is to divide, then add and subtract. Now, I'm going to kind of underline these together and these together because in order to go through there, when you are multiplying and dividing, it's interchangeable left to right. So if the divide comes first, left to right, you must do the division first, etc. But the other first two are kind of are exclusive with the P for parentheses and E for the exponents. The other way people have learned how to do order of operations is what they call GEMA. Again, G represents grouping symbols, not only parentheses, but you might have brackets or braces or something like that. E stands for exponents, the M for multiply and divide, and then the A for add and subtract. So that again kind of tells you with the multiply and divide that they do interchange. Whatever comes first, left to right, like I said, will be done first. So let's practice a couple of those. When we look at this expression of 3 plus 4x, we want to evaluate when that is x equaling negative 3. So what we're going to do is take this x equaling negative 3 and plug it in for that x. So I would take 3, just rewrite that, then 4 times a negative 3. Now there's two operations in this problem. This 4x here I should allude to. If there's not an operation with that, hopefully you remember from pre-algebra and algebra 1 stuff that means to multiply. So we have an addition and a multiplication here, and we would like to go ahead and do that multiplication first. So doing this piece, multiplying integers, remember that 4 times a negative 3 gives me a negative answer, and it would be negative 12, because 4 times 3 is 12. And then I have to go and do the addition of that. So when adding integers, remember, if they are different signs, you must subtract these two numbers here and give the answer the sign of the larger number. So 12, in a sense, is the larger number. It is negative, so the answer is going to be negative. When I do 12 minus 3, I do get a 9. So negative 9 would be the answer of evaluating that expression. Now, moving on to our second one, here I'm going to take this 4, and I'm not only going to plug it here, but I'm also going to plug it here for this x. So there's two places in this sense that we have to plug the 4. Now, it's nice that this one's not negative, because I don't have to worry about squaring that negative, which some people kind of get messed up on too. But we're going to plug in that 4, and so according to our order of operations, we don't have any grouping symbols. I know we have a 4 here with a parenthesis, but there's nothing inside there to simplify. So I'm going to go ahead and do my exponent first, which gives me 16. Then I'm going to just rewrite this, which you don't have to. You could go ahead and do the multiplication since we know that that's next. But just for here at the beginning, I like to do things step by step out so that you see it. Now go ahead and multiply our 3 times our 4, and I'm going to rewrite my plus 5. And here's where we come to the first left to right. It is subtracting going left to right first and then addition. So I have to, by the order of operations, to do the subtraction first, which gives me a 4. Then I'm going to add that 5, which in turn gives me the answer of 9. Okay? All right. Let's go one more on these evaluating operations. Extend that page a little bit. All right. Now we have an x and a y, so make sure that you are putting in a negative 2 for all the x's and a 4 for all the y's. So again, I'm just going to write it out here at first. 2 times a negative 2 for the x, then I put in a y, which is 4. Then on the bottom, when I have xy, remember that is assumed to be the multiply if I don't see any operation between them. So I need to do a negative 2 times 4 for the xy minus a 2 times a negative 2. So again, be very careful there with those negatives. All right, let's simplify the top, simplify the bottom, and then we're going to divide. So if I do 2 times a negative 2, well, 2 times 2 is 4. Positive times a negative is a negative, so I get negative 2 plus 4 on top. All over, in the bottom, I'm going to multiply and multiply first to simplify. So negative 2 times 4 is a negative 8. And then sometimes I'll write minus a negative 4, but if you think of this as a minus 2 times a minus 2, that in the end gives us a positive 4. So I'm going to go ahead and put that as a plus 4. So I hope that's okay for you. And if I want to write it out fully, really you get minus a negative 4, but right here this double negative becomes a positive, so you just get the negative 8 plus 4. All right, let's continue. Simplifying the top, negative 4 plus 4. If I owe you 4 and pay you 4, I'm back to even, so that's a 0, over a negative 8 plus 4, which is a negative 4. And then, be careful, don't let this trick happen to you. Make sure that you remember that 0 divided by any number is still going to give me 0, Do not get it confused as if you have something that looks like this, where you have 0 in the denominator. Remember that you cannot divide by 0, so this part here would be undefined. But for our answer, we're going with 0. Okay? All right, very good. Let's move on to our next page and start talking about real number systems. All right, so we're going to give out different sets of real numbers that we'll work with throughout college algebra, and hopefully you'll kind of tag on to some of them, and I'll give you kind of a visual representation here in a minute to hopefully help as well. So we're going to start off with the most basic, and we referred to them earlier as counting numbers, but they are also what is referred to as natural numbers. So natural numbers with a symbol of n, and sometimes they do kind of a funky little n, but I'm going to just remain at doing just a regular n. And these numbers are ones that are like, and I'll do set notation here, as 1, 2, 3, 4, etc. Okay? And again, there's some other examples. We can put 2, 3, 10, 20, 100, a million. All of those are counting numbers. Notice that they're all positive, okay? Now, if I take the natural numbers and add 0 to it, now I get another set. So if I kind of do 0, 1, 2, 3, continue on, then that is what we call the whole numbers. So the whole number set, usually referred with by a W, and so we could go as to do 201, 17, I don't know, 35. Those are all whole numbers. Don't forget that 0 is included. Now, when we do all of those numbers, but include their opposites, which would be the negative numbers of that, then that is what we refer to as the integers set. Normally, this is represented by a Z. Why? I'm not really for sure. And I is used for a different set, but I don't know where the Z comes from. But these are, I'm going to do kind of dot, 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 -3, -2, -1. Include the 0, 1, 2, 3. So it's basically the whole numbers and their opposites. So I could do something like -39, 496, etc., etc. All right, now, moving into a broader category is that we have numbers that can be written as a fraction of integers. So basically taking the set we just looked at and being able to put them as a fraction. Also as decimal forms, we can refer to them as these are our terminating and repeating decimals. Terminating means it stops. Repeat means it has a repetitive pattern to that. These are all what we refer to as our rational numbers. And again, it has a different letter. It's going to be a Q. And I'm going to give kind of an A over B here form where A and B are integers. And we have a fraction here, so we also want to make the condition that B is not equal to 0 here. Now, integers are going to be, or excuse me, the rational numbers, everything we've looked at so far can be considered a rational number because you can always put a number over 1 and make it a fraction, but we can also get into our other fractions. So I'm going to kind of do like -7, -1, 0, 5, 10, something like that. To look at some fractions, maybe I say 1/2, -3/4, 7/8. All of those will work. Any of the negatives will work. And in a decimal version, if I do like 0.6 repeated, which if you know that as 2/3, that can be written as a fraction, but as a decimal, 0.6 repeated. And maybe if I say like -0.25, that would be a terminating decimal in the form of a rational number. So those are kind of the numbers we're familiar with. All the rationals, decimals, fractions, and whole numbers and integers, negative numbers. But if we have a number that cannot be written as a fraction of integers, and it's a non-terminating, non-repeated number, then that is what we call irrational numbers. And this is the one that's going to be represented by an I. And I'm going to do some things over here. Pi, if you've ever done some geometry work, pi is one of our most famous irrational number. It never ends and it never repeats. Any square root that does not simplify down would be an irrational number. I could also do like a negative square root of 5 or something like that also. But I could also look at a decimal, and a lot of times when we do an irrational number, we kind of do a pattern in it, but it's a pattern that's not going to be repetitive. Okay, and the dot, dot, dot symbolizes that it is non-terminating. All right, so if we look at the whole number system that we have, all rational and irrational numbers put together, that is what we refer to as the real number system. A lot of times we do this little funky R, and this is everything that we've seen up here. Those are all of our numbers. Now, here's where I'm going to give you kind of a pictorial representation of our number systems. And so kind of looking at the big picture where we have all of our real numbers, which actually we will expand later on in a section here. And I'm going to put that funky little R to represent these are all the numbers that we know of so far. So going backwards kind of, we have our rational and our irrational numbers. Now remember, those were two separate things. And so I can't, in my picture, get those joined together. Now I'm going to put them as the same size, but that doesn't mean anything. That doesn't mean that there's the exact same number of irrational and irrational numbers, because if I were to guess, I'm probably going to say that there's more irrational numbers than rational numbers. So if we then go backwards, irrationals are kind of on their own, okay? But if you notice with our rational numbers, we did have the fact that we had our integers and our whole numbers and our counting numbers within that. So if we look over here with this piece right here, that gives us that as well. So I'm going to represent that. If I have rationals, well, our next one was integers, and so every integer can be written as a fraction. So I'm going to do kind of what we call as a subset of that and mark that as I. Then, if we go back to our whole numbers, which takes off the negative numbers, that means that all of those integers are also whole numbers. And we take away that 0, which means that my natural number set is my most smallest set there, and we can embed that basically within the others. So here's kind of a pictorial representation, which will allude to maybe helping us answer the next questions, where it says list all numbers from the given set that are natural numbers, whole numbers, integers, rational numbers, irrational numbers, and real numbers. Well, if we look at all those that we have in our set right here, then we can say that in letter F, all of those numbers are going to be real numbers. Now, where do they plop in? For part A, we're looking for natural numbers. Those were our counting numbers. So they had to be positive numbers and whole. So if I look here, I have a negative, so that's not it. That's a fraction, not a whole number. 0 is, remember, a part of the whole numbers, but not the natural numbers. Then we have a decimal. This is one of those radicals that cannot simplify, and this guy was our pi. If you look up above, that's going to be our irrational. And notice here, this is the square root of 64. Now, we haven't gotten into radicals, but you should have seen some of those before. As a reminder, the square root basically is asking us, what do we square to get 64? Or what number times itself gives me 64? Hopefully, you tell me that that number is 8. And so that number right there is the one that would be our only natural number in our set. So I'm going to put the square root of 64. Yes, that's equal to 8, but I'm going to write it as it is in the set. So we know that if we're going up to a whole number, that everything in my natural numbers is a whole number. So I have to have that square root of 64, but is there anything I can add to that? Looking at our chart, remember from natural number to whole number, we added this special number 0. So I'm going to add that in there. If it's a whole number, then it has to be an integer. So I'm going to again start with 64, square root of 64, and add in 0. But now is there a negative whole number basically that I can add in for integers? So there's 8, we're done with that. Pi is not, square root of 5 is not, that's not a whole number. 0 is already in there, that's not a whole number. And right here we have a whole number with a negative. So I'm going to add in that negative 11 right here as our integers. All right, section D is any rational numbers. Well, All integers are rational numbers. So I'm again going to start with the square root of 64, 0, negative 11, and I come up here and see, are there any fractions as integers? Ding, 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 this one right here. Or are there any decimals that are going to be terminating or repeating? And I hone in right here on this one. That is a terminating and repeating decimal. So I'm going to add in my negative 5/6 here and the 0.75 as my final rational number that I have there. Okay? Now, letter E are any irrational numbers. So those are, they can't be any of the ones we've talked about before. They are, so we've taken care of this one, this one, this one, and that one. So it has to be everything that's kind of non-repeating, non-terminating decimals, or like that square root that doesn't simplify, or our wonderful famous irrational number pi. So pi has to go here, and the square root of 5 also has to go here as well. All right, so now we've gotten taken care of letter F because we know that everything there is a real number. All right, so let's talk about comparing some numbers. Write ourselves what a number line looks like to get in comparing numbers and finding distances. So whenever I compare numbers, I'm looking at greater than, less than, greater than or equal to, not equal to. So determine whether or not this statement is true or false. I want to know, is negative 6 bigger than 2? Well, remember that the farther you go to the right, those are the bigger numbers. So actually negative 6 has to be less than 2. This is a false statement. If I look at negative 3, now negative 3 is right here, and negative 13 is down here somewhere. Is negative 3 less than negative 13? Well, again, the further to the right you get, this is the bigger number. So this also is a false statement. Now, let's look at negative 7. Negative 7 is right here. I want to compare that to the square root of 49, and it's actually negative. Now, remember what we said about the square root. What number times itself gives me 49? That is the number 7. So actually this side is negative 7 as well. Does that make it true? Negative 7 greater than or equal to negative 7? And the answer is yes. Be careful because this little underline here means equality. So if it was not there, this statement would be false. If it is there, this statement is actually true. All right, very good. Let's proceed on. We're kind of getting halfway here with our first chapter. I know there's a lot in this first section, but it is somewhat of review. So if you're having trouble with this, please come see me. All right, next our topic of discussion is the absolute value. And the absolute value of a number is what we refer to basically as the distance from 0. An absolute value here is going to always be positive if we're talking about it being a distance. Distance is never going to be negative, okay? So basically I'm looking at, if we think about our number line, I'm looking at here being 0 and I come down here to negative 3. What is this distance right here? Well, if I'm walking, there's 1, 2, 3 spots, so it is just a 3. So if your number is negative inside, then it becomes positive for the absolute value. If your number is positive on the inside, then it basically just becomes that number. Again, the distance is always going to be positive. Now, the absolute value symbol, I didn't mention that, are these bars, these straight up and down bars. So when you see that, that's what we're looking for. In a situation like this, we would need to simplify inside first. Again, a little bit of integer work. If you need to check it with your calculator, please do. Negative 3 minus 8, so it's like negative 3 plus 8, negative 8 if we add the opposite. And that gives me negative 11. And so the absolute value of negative 11, again, take that negative and make it positive. The answer is 11. More integer work. These double negatives on the inside here, 2 negatives multiplied together become a positive. So in reality, I have a 10 plus 2 here, which is a 12. Absolute value of 12 is just 12. All right, now we have an expression here dealing with absolute value. So again, I need to replace the x with -2, replace the y with 5. So I get the absolute value of -2 minus the absolute value of 5. Always rewrite what that is. Put those numbers in so you can see it. Absolute value of -2 becomes a +2 minus the absolute value of 5 is 5. Now notice I don't have any absolute values here. So it's okay once we do that first with our grouping symbols. Now I'm tasked with subtracting that, which actually ends up being a -3. 2 minus 5 is a -3, and that would be our answer. All right. So why is that important to know about absolute value? Well, it comes in when we talk about distance. Distance between 2 points on a number line, if I'm given two different values, call them A and B, then the distance between A and B is given by the absolute value of A minus B, or the absolute value of B minus A. So basically it's a difference, or you have to subtract both of those together and then take the absolute value. It doesn't matter the order, because in the end the answer will be the same. So given these 2 points from 3 to 18, when they're both positive, it's not too bad. Again, I always like to do the bigger minus the smaller, just so I don't have to work with a negative number. 18 minus 3 gives me a 15, therefore the absolute value of that is 15. The distance is 15. Here, I have two negatives. Well, that's not as easy as before, but again, I kind of, I just usually normally take the second one minus the first one. It's just kind of a habit. And here again, we have this double negative, which becomes a positive. So I get -14 plus 5, which actually is a -9. Again, if that's hard for you, check it on your calculator. And then making that positive gives me a 9. Okay? All right. Hopefully you don't have questions too much on that. And yeah, it's kind of a hodgepodge section here. We're going to move into some properties of these real numbers. What are things that we can and can't do? And this is going to help us when we're doing some of our algebraic work. And I'm just going to kind of give just the basic ones. There are others, but I'm going to waive some of those. The first one that we talk about is the commutative property. And these are the ones that are pretty much ones that you know you can do, but you just may not know the name of it. And so for addition, the commutative property, think about you commuting. You're moving, okay? And in this case, if I have A plus B by the commutative property, that means I can flip it over the plus. Now, you can also do that for multiplication, and the order of multiplying is going to give you the same answer. Now, notice I don't have anything here for subtraction or division because it doesn't work in that case. 3 minus 2 is not the same as 2 minus 3. Okay, so that's the commutative. Now, the associative property is normally referred to as the grouping symbol property because it doesn't matter the order with addition and multiplication that you add two things. Now, we're not switching it. We're just going to change the parentheses here. For addition and multiplication, doesn't matter the order in which you add those together, you're going to get the same answer. Likewise, if I do A times B first times C, that's going to be the same as if I multiply B times C first and then A. So for associative and commutative, we can only do those for addition and multiplication. The third property I have for you is the distributive property, and the distributive property is one we will use over and over and over, okay, when we start doing work with polynomials. So this is a property that I'm multiplying a number to two things on the inside of a set of parentheses. So this is going to be multiplied here with this and multiplied with that. So by the distributive property, I have to do A times B and add to that A times C. Identities. This is one that most people don't really remember the name of it, but we know we get this property to work. For addition, basically A plus what number kicks back A. That's going to give me the identity. And in this case, 0 is the identity. For multiplication, A times what number equals A back. Well, in multiplication, that number is 1. Therefore, 0 is the additive identity, and 1 is the multiplicative identity, is what we call that. And our last property is the inverse. The inverse basically is kind of reversing these two things. A plus what gives me the identity? Well, if I'm adding two things, I have to have the opposite of that number to make it go to 0. And A times what gives me the multiplicative identity, which is 1. This one's a little bit more trickier. This is actually a fraction. 1 over A is referred to as the multiplicative inverse of that. So the last two, I wanted to give them to you just so you have, but really the first three are the ones that we really use quite a bit. All right, so if we look, illustrate what property that it illustrates in this problem, we would be looking at here. What do I do to the first part to get to the second part? Well, looks like we've taken the 11 times the 8 and the 11 times the 2. Therefore, we could say this is our distributive property. And on this next one, order has changed actually. So I have this here and I have this here where we reversed over the multiplication. So hopefully you notice that as commutative. Don't get tricked by seeing those parentheses and automatically saying associative. So watch the order of things. Here we have 5, 3, 6. Over here we have 5, 3, 6, and the parentheses are moved around. Therefore, this is the actual grouping property of associative. Okay? All right. So we're going to use these properties to start by simplifying expressions. And we're just going to start off real basic with some of these simplifying expressions. And a lot of times we're going to be using that distributive property. So we're moving forward and review how to simplify expressions or combining like terms, that it is called sometimes. When combining like terms, labels do not change. That means the letters that I have there are not going to change. Only the numbers out front will change. And it says here you'll want to get rid of parentheses first, then combine as much as you can. And let's do by example. So starting with this first one here, notice I do have a set of parentheses. So again, by order of operations, we want to get rid of those parentheses by distributing. Now remember, it's a multiplying, taking 2 times that. So the label doesn't change when we're multiplying. We're just going to multiply the 2 times the 5x gives me a 10x, and then the 2 times the 4 gives me a positive 8. Now I'm going to tag on that minus 3. Now, what are like terms? I'm going to put all the x's together, all the numbers together, all the y's together, all the x squareds together. So in this case, there's not another x to go with that 10x. So I'm just going to rewrite it. But there are 2 numbers here that I can put together as a positive 8 and a minus 3 gives me a positive 5. So make sure you bring in that sign. Even though it's positive, we have to have signs that separate those terms. So that's as far as I can go in simplifying that expression. Let's do it again. Let's do it twice here with distributing. So I'm going to take 4 times 2 gives me an 8y. Positive 4 times a negative 6 is a minus 24. Then I'm going to take 3 times 5y, which gives me a 15y, and take a positive 3 times a positive 10, which gives me a positive 30. All right. What 2 things can I combine? I'm going to choose to combine this and this. Then I'm going to combine these 2 numbers together. So let's work with the y's. If I have a positive 8y, normally we don't write the plus here, plus the 15, again, number out front changes, but the label does not. So 23y. Then I'm going to do negative 24 plus that 30 gives me a positive 6. You can think of also as 30 minus 24. It all kind of interchanged together, and we can see it in different ways. So 23y plus 6 would be my answer there. All right, let's try this next one. Hopefully this first set of parentheses doesn't trick you out, but this second set just might. All right, so we're going to do 20 times x, because 4 times 5 is 20. Then we have a 4 times a negative 3, which gives me a negative 12. Now here, there's nothing in front of this set of parentheses. We think of it as an invisible 1 in front, But you can also think of it as multiplying it by a negative through to each one of those. So think of it as a -1 or just multiplying by a negative. Really, all that I do is change the sign there. So -1 times a +6 is a -6x. -1 times a +3 is a -3. And now I need to go forth and combine like terms. So I need to combine this x with this x. Then I'm going to combine this number with this number. And if you need to do these lines underneath, do so. So 20x minus 6 gives me a 14x. And then I have a -12 minus 3. So I'm at -12 on my number line. I got to go down 3. So they have the same sign. You have to add those numbers together and give the answer the same sign. So that gives me a -15. 14x minus 15. Again, if that's hard for you, please make sure that you check it on your calculator. All right, and our last one, I'll kind of change a color here so that we can see the difference, not run into that red one. All right, so here I've got two sets of parentheses. So you want to make sure that you work from the inside out. So I'm going to do this first, and all this other stuff I'm going to rewrite. 14x squared plus 5 minus 7 times a 1x squared, there's an invisible 1 there, gives me a 7x squared. And a +7 times a -2 is a -14. Now, that's only on those two terms. I do not have to multiply this +4 by 7. So I'm just going to rewrite the +4. And I need my grouping symbols also. That's very important. All right. Now, I'm going to go ahead and simplify inside here so that I can make it a lot easier for myself. So let's go 14x squared plus 5 minus, I'm going to open my parentheses. Can't do anything with that 7x squared just yet, but -14 plus 4. If I owe you 14 and I give you 4, that's a -10. And now we have one of these negative situations again. Remember, that's kind of like looking at a -1 in front. So I have 14x squared plus 5, and when I have a negative in front and I put it through here, really all it does is change the sign. This one's positive. It becomes a -7x squared. And then I have a negative times a negative becomes a +10. And I'm not finished yet because I need to combine these like terms here and here, and this and that. So 14x squared minus a 7x squared gives me a +7x squared, and a +5 plus 10 is a +15, and that would be my answer. Okay? All right. We have one last little thing before we head into section 2 on a different cast. And this is about doing more order of operations and simplifying. So this is a little different than what we saw before, more involved than what we had seen before. Don't forget PEMDAS, parentheses, exponents, multiply and divide, add and subtract, or you can think of it as GEMA. All right, so here I don't have any parentheses in this example, but I do have some exponents. So I'm going to go forth and just do those exponents. Now remember, exponents, you take 10 and multiply it by itself 2 times. So 10 times 10 is 100 minus this 100. Now be careful, don't subtract it just yet. Divide by 5 squared means I need to do 5 times 5, which is 25. Times 2 minus 3. Now, don't go too fast here. This is where we have to assist now. No more exponents. We're done with that. We're done with that. Now we have to look here. Collectively, between left to right, which comes first, multiply or divide? So I'm looking here, left to right, there's a minus. Then there's a division. I have to do this part first. So I'm going to rewrite the 100. And if I do 100 divide by 25, I get 4, and I'm going to rewrite the rest. So don't do too much here in your head. Now, we have 2 subtractions and a multiply. So the multiply has to come first, so I have to do this part first. Again, I'm going to go 100 minus 8, which is the product of 4 and 3. And now I go forth and do my subtraction. So technically, this one left to right has to be done first. That's a 92. Minus a 3, and my final answer here is 89. Okay? And our last problem is section 1. I know this is kind of long, but again, it's a lot of little things added into one previous or review section, I guess you could say. All right, so with this fraction, you want to simplify the top, simplify the bottom, and then do the division for that fraction bar. So I'm going to do kind of the order of operations on the top. Yes, I'm going to kind of come down here and do them separately, but I'm going to do this division first. So we need to do 10 divided by 2, which is 5, plus 3 times 4. So again, don't do too much. In here, I have a minus and a multiply. So the multiply is what comes first. So I'm going to write that as 12 minus 3 times 2 is 6. Don't forget the little square outside. All right, so looking at the top, I'm going to come down here. Between add and multiply, I have to multiply first, so I'm going to go 5 plus a 12 when I multiply those. Underneath, I'm going to do the parentheses, which is 12 minus 6, which gives me a 6. Then I have to square, and we are getting oh so close. 5 plus 12 now on the top is a 17, and a 6 squared, don't forget that's not 6 times 2, it is 6 times 6 twice, and that gives me a 36. And the question here would be, can I simplify this fraction? And the answer is no. Therefore, that is my answer. So that is it to section 1. We're going to evolve past that a little bit and get into some exponents, which includes also some scientific notation. So thanks again for participating in section 1. We'll see you in section 2.